Okay, mm, let's start with solutions. So we all know that mixtures can be homogeneous as well as heterogeneous. Now when we say it's a homogeneous mixture, then homogeneous mixtures are classified into colloids and solutions. So we'll try to understand what are solutions. Now usually in solutions we have two components, that those are the solute and solvent. Now, what are solvent and solute? Then we can say that if in a mixture the 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 amount which is in smaller quantity is usually called as the solute, and the amount in larger quantity we usually refer to as the solvent. Now when we mix a solute in a solvent, then that how much amount of solute goes into the solvent is determined by the concentration. And this concentration can be calculated by mass percentage. By knowing the mass percentage, we can have molarity, normality, and um, mole fraction. So these are the techniques that we employ for determining the concentration of a particular solution, or simply put, how much solute is added to the solvent, or how much solvent is there in that particular solution. We can calculate, or we can get an idea by knowing the concentration, and the concentration is determined by these factors. Now when we say mass percentage, or the percentage concentration, there are some various ways to calculate it. Suppose if it is percentage then we go for weight over weight, which is given by percentage of weight over weight, which is given by weight of solute over weight in grams, weight of solution in grams again in 100. That's the weight over weight percentage. That's how we calculate. And if it's percentage of weight per volume, then we can say gram of solutes over volume of solution into 100. That is how we calculate percentage of weight per volume. And if it's volume per volume, then it's we can calculate by volume of solute over volume of solution into 100. That's how we calculate the different percentages of the mass in a solution, or to find the concentration. Okay, now what is molarity? It's denoted by capital M. Molarity simply means number of moles of solute per liters of solution. So if we say M molarity, then we can calculate by the number of moles per volume of the solution into 1000. Volume to be in ml. So number of moles of solute per volume of the solvent into 1000. That gives us the molarity. Or this number of moles is given by weight of the substance divided by the molar mass of the substance. So mv into 100,000. That gives us the molarity. Now what is molality? Molality we denote by small m. So molality is defined as the number of moles of solute per 1000 grams of solvent. So it's similar to molarity. The difference is we use instead of liters, it's per kg. Here it's in terms of liters, but here in terms of kg, the solvent. So we can say that the molality is given by the weight over mass into 1000, in grams into 1000. That is the molality. And normality we denote by n, and normality simply means number of gram equivalents of solute dissolved per liter of solution. So normality is equal to number of equivalent of solute per volume of solvent. That is normality. What about mole fraction? What are mole fraction? It is a ratio. It's just a ratio. Mole fraction is just a ratio between the number of components present in a solution. Suppose there are two components. Suppose mole fraction usually denoted by chi. Mole fraction. Suppose there are two components, say sodium chloride. So there is sodium and there is chlorine. So to find the mole fraction of sodium, we simply mole fraction of sodium, it's equal to sodium, the molar mass of sodium divided by the molar mass of sodium plus chlorine. That's how we calculate the mole fraction. If there are more components, then we'll simply divide one component by the rest of the sum of the rest of the components in that particular compound. That's how we calculate the mole fraction. Okay, let's try to solve this problem. So they've given us 10 mole solution. So we're asked to calculate the mole fraction of urea and the percentage of weight per weight of urea. So they have given us 10 moles of urea in 1000 grams of water. 10 mole solution means 10 moles of urea in 1000 grams of water, molality. Now mole fraction of urea would be given by here in this particular solution we have urea and then water. So they've given us 10 moles of urea. So to find the mole fraction of urea, so 10 moles divided by 10 plus, now water, it's given us 1000 grams. So 1000 grams divided by the molecular mass of water, it's 18. So which gives us, if you calculate, 0.15 to 6. So that is our mole fraction of urea. Now, percentage weight per weight of urea would be given by 10 molar solution into the molar molecular weight of urea divided by molecular weight of urea plus 1000 grams of water into 100. So that gives us around 37.5% of weight percentage. So that's how we calculate mole fraction and weight percentage. Okay, another question to find out the molarity of calcium carbonate, aqueous solution which has concentration of 200 parts per million. So what is parts per million? That means 200 parts per million simply means 200 grams of calcium carbonate in 10 raised to the power 6 or a million. This is 10 raised to the power a million gram of water. So since the molar mass of calcium carbonate is approximately 100, so to find out the number of moles of calcium carbonate, we just divide it with the molar mass, 100 grams, so which is equal to 2 moles of calcium carbonate in 1 liter of water. Now, so molarity, therefore molarity will be given by 2 divided by 1 liter is 1000, which is equal to 2 into 10 raised to the power negative 3 molar. So that is how we calculate the molarity. Again, solutions can be dilute or non-saturated, saturated, and supersaturated. If the number of if the number of solutes in the solvent is very less, then we say it's non-saturated or diluted, very dilute solution. But if the number of solute, if we keep on adding, then it becomes saturated with the solute. And when you go on further adding the solutes, then there'll be a time when you cannot further add any more solvents. Then that solution is said to be supersaturated, and that solubility, that means addition of solute to the solvent, is called the solubility of that particular solute in the solvent, is governed by the pressure as well as temperature. Now, the dependence of pressure is governed by Henry's law. And but before going to Henry's law, let's try to understand something on this pressure. So let's imagine a liquid or a solution in a container. So on the surface of in a container, so a closed container, suppose, so let's closed container, so we have the liquid here. Now, some of the molecules on top of this on top of the solution will escape, will lose the attractive forces, and then will escape. So they'll be, but since it's a closed vessel, they'll be bouncing of the walls, the molecules of the solution that have escaped. And these, after bouncing, they'll come, some of the molecules may come near to the solution, and then again it becomes it'll get ethered, or it'll get attached back to the solution, and that phenomenon is called what we call condensation. And when the amount of uh, when the amount of, or the number of molecules escaping from the surface and coming back and getting attached to the surface becomes equal, that is what we call the equilibrium state. And during during the process, when it escapes, it bounces off the walls. The molecules, the gas molecules, will exert that that bouncing off will exert pressure, and that is what we call as vapor pressure. Vapor pressure. And that is how pressure is generated in from a solution or from the surface of a liquid. So how to define vapor pressure? So we can define the vapor pressure as the partial pressure of vapors in equilibrium with pure solid or pure liquid at a given temperature. And suppose there are more than or there are different components in that solution, then uh, all the components will exert different pressure. Suppose if we have uh, an acid in water, then the vapor pressure of the vapor pressure of pure acid and the vapor pressure of pure water will be different from the that solution between the acid and the water. So we calculate by partial vapor pressure. So partial vapor pressure is nothing but the pressure, the pressure of the different vapors over divided by the total pressure. Now in uh, we know that solute and solute is dissolved in solvent to get the solution. So solutions can be made from solid and liquids, or gases and liquids, or liquid and liquid. So now especially solubility depends on one factor: solubility. So solubility, it depends on one factor. That means, or simply put, we can say that like dissolves like. Like dissolves like, meaning if uh, if if the solute is polar, then it will dissolve in a polar solvent. Or if it is a polar liquid, then it will dissolve in a polar liquid. So goes with the non-polar solute and a non-polar solvent. A non-polar solute will be dissolved only in a non-polar solvent. Similarly, a non-polar liquid can be dissolved with a non-polar liquid. So that means like dissolves like. You cannot dissolve a non-polar solute in a polar solvent. They are immiscible. 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 That means they don't mix. And if they mix, we call as miscible. Miscible liquids or miscible solution, and so on. Okay, now let's talk about effect of temperature in the solubility of solutions. Now, we know that suppose when if the solute and the solvent, suppose solvent gives us solution. Now if this reaction is exothermic, that means our enthalpy change is negative, exothermic, then as temperature increases, then solubility, this solubility decreases. But if it's an endothermic reaction, that means if our enthalpy change is positive, then as temperature increases, solubility goes up. That is how temperature affects the solubility of a particular reaction. Okay, then let's move on to solubility of gases in liquids. So there are four factors that affects the solubility of gas in a liquid. Number one is the nature of the nature of the gas. Then we have nature of the liquid, and of course temperature and pressure. So these are the four factors that affects the solubility of gases in liquids. Now, as I've mentioned, solubility of gases in liquids is governed by Henry's law. So let's try to define what is Henry's law. So the statement is solubility of a gas in a liquid at a given temperature is directly proportional to its partial pressure at which it is dissolved. So according to Henry's law, partial pressure of each of the components is essential for determining the solubility of any gas in a liquid. So by the definition itself, partial pressure is directly proportional to the mole fraction. So we can remove the proportionality by putting a constant. So KH is equal to P over the mole fraction. So this K sub H is our Henry's law constant. Okay, let's try to solve this problem on Henry's law. So they've given us the Henry's law constant for oxygen dissolved in water, and they've given us a partial pressure also. So they're asking us to calculate the concentration, that is the molarity of oxygen dissolved in water. So here Henry's law constant is 4.344 atmospheres, and then the partial pressure of oxygen is 0.4 atmosphere. Now, according to Henry's law, we know that KH is equal to over the mole fraction. Now, the mole fraction of oxygen is equal to, given us the partial pressure over 4.34 into 10 raised to the power 4, which gives us 9.2 into 10 raised to the power negative 4. So that is the partial mole fraction of oxygen. Moles of water. Number of moles of water is given by number of moles of oxygen divided by number of moles of oxygen plus number of moles of water. Mole fraction of oxygen. sorry, this number of moles, mole fraction of oxygen. So mole fraction of oxygen is equal to number of moles of oxygen over number of moles of oxygen plus number of moles of water. Now this number of moles of oxygen is very negligible compared to the number of moles of water. Therefore, mole fraction of oxygen is nothing but number of moles of water. So number of number of moles of oxygen is equal to the mole fraction of oxygen plus number of moles of water. So if we plug in the values, then we'll get the result. So it's equal to 9.2 into 10 raised to the power -4 plus this number of moles of water is nothing but 1000 divided by 18. 1 liter of water divided by the number of moles of the molecular weight of water. That will give us 55.55. So our 5.11 into 10 raised to the power -4 moles. So these are molar mass. So the applications of Henry's law and the limitations of Henry's law will be is presented in your book, so I suggest you go through those. Then we'll continue with the immiscible liquids in the next video.